Hello and welcome to a hopefully interesting video exploring the distribution of runtimes for squaring a number in Python and also taking its exponential. So in the previous video we actually got this histogram right here that shows a log-log plot of the probability of getting a certain runtime when you square the number pi and we take its exponential. Interestingly, we can see there's sort of a linear behavior going on here generally, which indicates that we have some kind of power scaling going on. Maybe the probability density scales as 1 over t squared or something like that. We're going to find out what does that scaling actually look like. So to do that, we are first going to get all the raw data out right here. So instead of actually plotting a histogram here, we're simply going to use the np.histogram function with the raw data and the bins that we specified earlier in order to get the probability density and the bins out as simply numpy arrays. And we can do that both for the data for the squaring and the data for the exponentiation. Then we can plot the probability densities like so, fairly simply. So now we can sort of treat them a bit like data points and then fit a model to them. Now one thing we might want to do to make this a bit more accurate is to actually discard all of the values that are corresponding to very low probability density. Here we actually have, I think we took a total of 1 million samples. So all of the points down here only correspond to maybe 1 or 2 samples, which isn't really a lot of data to work with. And like those data points aren't very accurate and very reliable, so we shouldn't really include them in the fit. So somehow we need to extract those and filter them out. To do that, I've specified a threshold with a certain cutoff value here. Then we're going to use the np.where function with the probability densities to determine which probability density entries are above this threshold. So now we just get the list of indices in this array. Then we can use those indices to extract the bins corresponding to values that are above that threshold, as well as the actual values that are above that threshold, like so. So using that, we can simply plot the filtered data like this, and we see we get something that's a bit more clean like this. So now we want to fit some kind of linear model to this in the double log domain. So that will be a model of this type here, and we can implement it very easily by simply taking the 10 log of both the bins as well as the probability densities like so, and then fit a linear model to it and plot it. So we can do that both for the data for squaring the number pi and for taking its exponential. If we do that, we should get a plot out that looks like this. Alright, so you can see that definitely there is some kind of linear scaling going on in the double log domain, which tells us that this model here basically looks like, well, b times x to the negative 2.5, 2.7 or something like that. So there is kind of a power scaling going on. So what sort of distribution is this even, and does it have a name? It turns out it does. It's called the Pareto distribution, and basically it looks like this. So we have a certain sort of scaling factor, alpha, that's what we found earlier to be, 2.5 or something, 2.7. And then we have a minimum value. And if you think about it, it kind of makes sense that it would follow this distribution at least for a single computer operation, because there must be some kind of minimum time spent by the CPU, like setting up the calculation before it actually executes it. And then there'll be sort of a tail, because maybe there's some other processes going on, or for some reason it just takes longer. I actually don't know exactly what determines the CPU runtime for a single operation, but you can sort of imagine that this is maybe a realistic model. And we can actually check that it seems to follow it, because we can just sort of define the Pareto distribution here, and then plot it alongside the data we got here. So you have just specified sort of manually a value of 2.75 here, and then we can plot the actual raw data along with this model for the linear scale and the log scale and the double log plot right here. So that seems pretty reasonable. Actually, before I go, I should probably clarify that we only get this Pareto distribution when we're measuring the runtime of a single operation, like we did here, measuring the runtime for squaring pi or for exponentiating pi. But if you're measuring the runtime of a more sophisticated function with a large number of different operations inside, probably you're going to get something that looks more like a Gaussian because of the central limit theorem. This effect in statistics basically tells you that if you have a large number of random numbers drawn from different distributions and you average them together, then in the end the distribution of runtimes, whatever it is going to be converging towards a Gaussian. But in our case we only have a single distribution involved, which is the Pareto distribution. But if we were to, let's say, take the probability of running, let's say, 100 squarings, for example, then we'd actually convert to something that's more like a Gaussian. So anyway, hope you found that useful. Check out the source code in the description, and I'll see you in the next video. Bye bye.